Greetings, students. So I wanted to try something a little different here. I'll give you a little bit of video feedback on one of our recent assignments that relates to bond type and polarity, predicting whether or not poles would form on molecules. And what we'll come to learn is why that's significant in some future lessons, what that has an effect upon. So let's get right to work. So what we see are a listing of pairs of elements. We're to use the electronegativity values of each of these pairs of elements to determine what type of bond might be present. So let's get started with boron and chlorine. So if we're looking at the elements boron and chlorine, we're looking for boron on the periodic table, electronegativity 2, chlorine electronegativity 3. The difference between them allows us to make a prediction. So the difference between 3 and 2, right, we just subtract 3.0 minus 2.0, and we end up with 1.0. That should say minus, not equals. There we go. And a value of 1.0 for electronegativity difference. Now we can compare that to this guide right here that tells us that if the range is from 0.41 to 1, we get a kind of polar covalent bond. It says it's slightly polar. We're not going to deviate from either being polar or non-polar with slightly or very. We're just going to call it polar. However, slightly means the attractive force on the poles would be lesser than if it were a very polar covalent bond. So let's take a look at actually marking that up correctly then. So we would call this, right, polar covalent. Okay, so we do the same thing for each, C and H. So we'll go to our electronegativity table, right? The value for C is 2.5. The value for H is 2.1, right? The difference between them allows us to calculate, right? So the difference, 2.5 minus 2.1, the difference is now 0.4, and we'll go back and consult the chart. 0.4, we'll look at that. That puts us in the region of non-polar covalent. So no attractive force or weak, very weak attractive force would be present on a molecule that is non-polar covalent bonded. So we can go back and mark that one up now, and we'd call that non-polar covalent. Okay, and we're going to mark each of these in the same manner. So barium and fluorine. So we'll go to our chart here, barium, which is right down here, 0.9. Fluorine, the highest electronegative element, 4. So we'll subtract those two, 4 minus 0.9, right, 4 minus 0.9. And that comes to a value of, what is it, 3.1. So when we consult the chart for that, we're going to find out that that is ionic, right? Greater than 1 point. So very strong attractive force, right? So particles that are ions have strong attractive force for oppositely charged ions. So we will call that guy ionic. H and O. So H and O, when we go and consult our chart, H is 2.1, O is 3.5. So the difference between 2.0 and 3.5 is what we're interested in. 3.5 minus 2.1, right? Again, that is 1.4, not 2.4. That's going to put us in the range of polar covalent. So let's just verify that. There it is, right? 1.4 falls between these two values. So we get a polar covalent bond, happens to be very polar. So strong attractive poles. So polar covalent. P and S. So P and S, we go back to our table. P is 2.1, S right alongside of it, 2.5. So 2.1 and 2.5, right? So let's list the highest one first so that we don't get a negative value. The difference is 0.4, which we've seen before up above, right? That would be non-polar covalent again. Right, when that difference gets to 0.40 or below, it tends to be non-polar covalent. C and S. So C and S, C is 2.5, S is 2.5. Interesting. Same electronegativity value. Well, the difference there is going to be 0. 2.5 minus 2.5, right? 0, right? So once again, non-polar covalent, right? That falls in that range. If I just were to show you here again, right, that falls in that range of right here, right, 0.0 to 0.4. So non-polar covalent once again. And our last example here, nitrogen and oxygen. So nitrogen and oxygen, and we'll consult our electronegativity table. Nitrogen 3.0, oxygen 3.5. So the difference between those two, right, 3.5 minus 3.0, 0.5. So that's going to put us in the region of polar covalent, but slightly polar. So weak attractive poles along the surface of the molecule. So, but again, we'll just call it polar covalent. We get that there are degrees of polar covalent. Okay, so that's what we were asked to do in this first part. Second portion asks us to determine, rank the polarity from lesser to greater. So the number 1 being the least polar, to number 4 being the most polar. Well, we already just did this N and O. So I'm just going to put down here the value of the difference was 0.5. We're going to look at Si and C. We'll go take the difference in electronegativity. Si, silicon 1.8, and C 2.5. So the difference there is 0.7, 2.5 to 1.8, right? We just subtract those two things. So 0.7 difference in electronegativity. Boron and phosphorus. Boron is 2.0, phosphorus is 2.1. Wow, really low difference. Difference of 0.1, right? So 0.1, and K and Cl. So K and Cl, right? Our value for K, 0.8, our value for Cl, 3.0. Subtract and make the difference. That would be 2.2. So this would be 2.2. What this allows us to see is which is the least polar molecule and which is the most polar. Well, B and P is non-polar covalent because the value is very close to 0. So this would get our 1, our least polar, right? The smallest difference in electronegativity, right? This guy here would be our second lowest polar, and our third, and finally our fourth. Okay, last thing it asks us to do is to identify the location of the poles or the charges along the poles. So there's a partial minus charge for polar covalent bonds and a partial positive charge. The minus charge is always closer to the atom with the higher electronegativity. Oxygen had a value of 3.5, and looks like nitrogen had a value right here of 3.0. This was nitrogen and oxygen. We've already done that. So it looks like oxygen has a greater electronegativity. It attracts electrons better. So the oxygen is the partial negative pole. The nitrogen side would be the partial positive pole. And that's how we make that determination. So silicon and carbon, if we forgot, we could go back and look that up, right? Silicon and carbon. We just want to see silicon was 1.8, carbon was 2.5. So carbon has the higher electronegativity. Carbon will be the partial minus pole, right? Silicon will be the partial positive pole. we're not going to do that at all for B and P because it's a kind of bonding that's called non-polar covalent. So we don't get partial charges to form. And for K and Cl, well, this would be ionic bonding. And because it's ionic bonding, we don't have partial charges, we have complete charges. So the Cl has the much higher electronegativity, that would be the negative ion. The K would be the positive ion. So there's no sigma symbol or sigma symbol with positive charge located alongside of it. So that Greek letter with the charge is not necessary for ionic compounds because there are no partial charges, there are complete charges. And then lastly, the last thing was, how do we look at a molecule and tell from its symmetry if it would be polar or non-polar? So what I like to say is, look for multiple lines of symmetry. For example, this guy right here, if I cut the molecule in half and fold it in, there's a beautiful line of symmetry. If I do it in this direction, once again, I get a perfect line of symmetry. So multiple lines of symmetry typically mean something, typically mean non-polar molecules. So 2 or more lines of symmetry, non-polar. This guy here, the way it's drawn, I might argue that maybe these dots should be drawn over here, and that might give us 1 line of symmetry, but certainly we're not going to get more than a single line of symmetry on that molecule. So that's not multiple lines. That molecule would be polar. In fact, it's pretty well illustrated here that there's a lot of minus charge on this side, partial negative charge over here because of these lone pairs of electrons over there. So that lone pair of electrons tends to cause that. So if we look at a water molecule here, we could kind of say, oh, look, we could cut it in this direction. And that would give us 1 single line of symmetry. But again, that's not multiple lines of symmetry. So that tends to unevenly distribute the valence electrons along the surface of the molecule when that happens. And we end up with a polar molecule as a result. So I hope that you found this useful and you got some good feedback about your recent work on this assignment. And I'll be talking to you real soon. Have a great day, folks.